That's actually it for Monte Carlo simulation, except for one thing, which is how many simulations should you do? So I said 100, but I also said 1,000. I also said 1,000,000. So which one is it? Well, it depends. And I'm going to tell you how to calculate the number that you need. And this is something that I've never seen anywhere in any textbook other than the one that I wrote, but that was for financial econometrics. Nobody in the literature has ever said how many simulations do you need. So I'll tell you how to figure that out. It has to do with the central limit theorem, which is like this really incredibly magical, beautiful result that I think, did you guys cover central limit theorem by show of hands? How many people? Yeah, okay, good. At one time, I think it was Paul Samuelson who said that, you know, if you encounter the central limit theorem for the first time, you either think it's beautiful or you don't. And if you don't, I feel sorry for you. So I think it's one of the most beautiful results in all of mathematics. And so let me use it now and describe to you how you can use this to figure out how many simulations you should do. All right, so let's start with the estimation of the expected risk-adjusted NPV. This is the thing that we don't know and we want to estimate using our Monte Carlo simulation, right? Now by the way, let me go back and describe to you why it is that we even care about that. So remember from last time, when we want to calculate this, the random variable here is x, right? And x is just really one random variable. I've got a bunch of x's every year, but as we said last time, either it's going to be 100 or 300 from this point forward forever. So we only have one random variable, right? It's this Bernoulli trial. And so the way we calculate this expectation is there are just two possibilities. Either it's 300 or 100, and then we calculate the sum, and then the max, and then we weight that by the probability that it's 300 or 100. So we can actually evaluate this expectation explicitly if we have a Bernoulli trial. But if I tell you that this distribution, this x, is some really complicated, gamma distribution, you actually can't calculate this very easily. It can be quite complicated to do that. And if you have multiple decision points, so that, for example, after phase 1, you've got one realization of what the value of the compound is. After phase 2, you've got another realization. After phase 3, you've got another. You've got 3 random variables in sequence, and then you make decisions based on that. Very quickly, you will not be able to calculate this expectation analytically. You can't get a solution for it, okay? But Monte Carlo simulation allows you to estimate it by running a lot of these experiments and then averaging them. And we know that the average converges to the theoretical value with a large enough sample. That's what the central limit theorem says, and the law of large numbers. So the law of large numbers says that this expectation estimate converges to the theoretical expectation with a large enough number of simulations, right? But the central limit theorem says something even stronger. It says that if you look at the difference between the estimate and the truth, and then you multiply that by the square root of m, then this quantity, if you have a large enough m, this converges to a random variable that is normally distributed with mean 0 and some variance sigma squared RNPV. So this is the central limit theorem right up here, okay? That's what the central limit theorem, and this little a stands for asymptotic. It means in the limit, as m gets really, really big, you've got a normal random variable, okay? That's important because what it allows us to do is to say that the standard error of this estimator, so our estimator of the actual expected RNPV, that is a random variable that has its own standard deviation, which we call the standard error. And the standard deviation is sigma RNPV divided by the square root of m. Okay? So just to be clear, I've got this estimator of my RNPV. And let me just give it a different letter because I'm tired of writing that whole thing out. Let's call it, I don't know, how about Q? So Q is this estimator of the actual expected RNPV that I really want to know about. How close an estimator is it? How accurate is it? Well, it's a normal distribution. And I know that it's going to be unbiased. It's going to eventually converge to the theoretical correct Q. So I just need to know what this is in order to get a sense of how accurate my estimator is, right? And I just showed you from the central limit theorem that this standard deviation is given by the standard deviation of the individual simulations divided by the square root of m. Okay? Now, I don't know what this is, but I can estimate it. How can I estimate this? Can anybody tell me? I run a whole bunch of these simulations, and, yeah, Jose?
Yeah, when essentially you have all the results of the RMPV, you have the distribution, so you can calculate this.
Exactly, right. You got 100 of these numbers, right, from my simulation. Calculate the variance of that set of realizations. That's an estimate. So if you calculate the variance of that sample of 100, that'll give you sigma hat squared R NPV. So now, if I take that and plug it in here, this will tell me what my standard deviation is around the truth. So suppose I simulate this and I calculate a mean of 400 million. If I actually calculate the standard deviation and the standard deviation of my estimate is plus or minus 100 million, is that good enough for you? Or do you think that that's a little bit too noisy an estimate of the theoretical truth? 400 million plus or minus 100 million, good or bad? Let me put it another way. So suppose that you're about to see the CEO and you're proposing your project which has an expected value of 400 million, but the standard deviation is 100 million. So it's going to be 400 million plus or minus 200 million. Are you comfortable talking to the CEO about this? No, that's too big. So that means that you didn't do enough simulations. So let's crank them up. Let's crank up the simulations. Suppose instead of having a standard deviation of 100, I wanted to reduce that to 10. I wanted to reduce the number by a factor of 10. How many more simulations do I need to do in order to achieve that? How would you calculate that? This number is 100. I want it to be 10. So I have to increase m by how much? Right, exactly. So if I've started 100 simulations, I need 10,000 simulations. And then what I'll get is 400 million plus or minus 20 million with 95% probability. That's pretty good. If you really want to be ultra precise, do 1,000,000 simulations. Because then you'll get, this is 400 million plus or minus 25 cents, which now you're getting absurd, right? Anybody who thinks things are that precise obviously doesn't understand these kinds of assumptions. So in order to figure out the level of accuracy, you simply need to estimate the standard deviation and then calculate the sample size so that you get within the degree of precision that you would like. That degree of precision drives the number of simulations you want to do. And these calculations are all approximations based upon the central limit theorem, but because your simulations are independently and identically distributed, they're going to be fantastic approximations. And so you don't need a lot in order to get to asymptotic land here and to be able to apply these results, okay? So you now know how to do simulations, you now know how to interpret simulations, and you now even know how many simulations to do. You can therefore go forth and apply in lots of different settings. What I think you'll find from these simulations is that it's just an incredibly useful, powerful tool to get a quick answer. If you try to use decision trees every time, you're going to be left in certain cases with lots of complexities that you can't easily resolve and calculations that you can't do, particularly if you've got complicated negotiations with license deals where payments kick in, milestones disappear, and various kinds of triggers for contract clauses. simulations are generally going to be easier to do, but they suffer from the disadvantage that you have to make a statement about the nature of the uncertainty. Is it normal? Is it log normal? Is it beta? You have to know a lot more about the distributional assumptions, and they'll have an impact on how you interpret the results.